Okay, so we know that all the states that have a particular principal quantum number will have the same energy, because the energy only depends on the principal quantum number. Okay, so let's just kind of list some of these. So when our principal quantum number is 1, then L can only go from 0 to n minus 1, so it can only go from 0 to 0, that is, it can only be 0. And M, or M sub L, can go from minus 0 to 0. Okay, so it can only have one value. So we only have one value for M. And so the degeneracy here, we only have one state. It's 1, 0, 0. The degeneracy is 1. That is, there's only one state with that energy. And in spectroscopic notation, which corresponds to how we usually designate these orbitals, these states in chemistry, that would be a 1s orbital. Okay. Now if we go to n equals 2, okay, then L, we can have L equals 0, or we can have L equals 1. Okay. If we have L equals 0, again we can only have M equals 0. If we have L equals 1, we can have M equals 0 or plus or minus 1. Okay, so here we have one state. Here we have, this is getting messy. Let me see if I can do this a little bit neater. This can be 0 or plus or minus 1. Here we have one state. Here we have 3. And so the total degeneracy is 4. Okay, and this would correspond to either a 2s if L equals 0, or a 2p if L equals 1. Okay, now if we go to n equals 3, okay, then we can have L equals 0, 1, or 2. Again, L can go from 0 to n minus 1. Again, for L equals 0, M can only be 0, so we have only one state there. For L equals 1, we can have 0 or plus or minus 1, so we have 3 states there. Okay, and for L equals 2, we can have 0, plus or minus 1, and plus or minus 2, and so we have 5 states there. So all in all, we have 5 plus 3 plus 1, we have 9 states. That's the degeneracy. And the this n equals 3, L equals 0 state would be a 3s orbital. The n equals 3, L equals 1 would be a 3p orbital. And the n equals 3, L equals 2 would be a 3d orbital. Okay. Again, now if we go to n equals 4, okay, we can have L equals 0, 1, 2, or 3. Okay. If again for L equals 0, we can have only M equals 0, so that's one state. For 1, we can have, oops, don't need to write M equals. We can have 0 plus or minus 1, that's 3. 0 plus or minus 1 plus or minus 2, that's 5. And 0 plus or minus 1 plus or minus 2 plus or minus 3. Okay, and that's 2, 4, 6, 7. Okay, and so we have 12, 16. Okay, is the degeneracy, and again, this would be a 4s orbital, a 4d orbital, a 4p orbital, and a 4f orbital. Okay, and this structure of the hydrogen atom provides a clear understanding of the periodic table of elements, but of course this is also modified by the fact that the degeneracy is different when you add in other electrons.